The team here in Mission Control is still assessing exactly how the problems with the cooling loop will be affecting the schedule for the station's upcoming events, including the launch planned for next week of the Cygnus vehicle. But once the Cygnus vehicle does go, it'll be carrying to space several new experiments for the space station. And we have with us today via phone Dr. David Klaus to tell us about one of those experiments. He's the principal investigator for the NPL Vacccine-21 experiment, and he's with the University of Colorado. Dr. Klaus, thanks so much for joining us.
Oh, my pleasure. Thanks for inviting me.
Well, why don't you tell us a little bit about what this experiment is?
Okay, first of all, the payload name is a little misleading. It was manifested under this. We were looking at vaccine development in recent flights. This one, rather than changing the name, we're slightly doing a different experiment. It's looking at antibiotic effectiveness in space. So not so much in developing a vaccine against, say, a viral infection, but in looking at antibiotics that would be used to treat bacterial infections.
Okay, and I think we have some past research that indicates that they do work a little differently in space than they do here on the ground, right?
There's a number of different phenomena that have been shown to occur, starting with bacteria tend to grow better in general in space. They begin to grow a little sooner in the lag phase period, and they reach higher final population densities. Other earlier studies have also shown that their bacteria are able to grow in the presence of what would normally be an inhibitory level of an antibiotic in a microgravity environment.
I'm sorry, can you repeat that last part? I didn't quite understand the last sentence there.
Well, normally, antibiotics are used to kill the bacteria, to treat bacterial infections. But in a microgravity environment, for a variety of reasons that are not yet fully understood, it takes higher concentrations of the antibiotic in order to inhibit the growth or to kill the bacteria in space.
Okay. That's obviously something that we would be interested in learning more about for a number of reasons.
Yes, correct. First of all, first and foremost, I guess, is for the protection of space travelers on long-duration flights. We want to have a better understanding of what's going on there. But also for terrestrial applications, there's a number of people in the U.S., I think the number is around 100,000 Americans each year die from bacterial-resistant infections. And this is, a huge financial burden, not to mention the loss of life. And the study that we're looking at is trying to understand a little better of how the bacteria acquire these drug-resistant mechanisms in the first place by watching, observing, and characterizing how they respond to the spaceflight environment where they seem to do it better.
And so how do you study that in space? I'm assuming, obviously, we don't infect the crew with something and then give them the vaccine. So how do you do that?
Correct. This is all done via our microgravity test tube devices that allow the crew to mix these cells into the antibiotic concentrations, and we basically have it set up so that the bacteria are going to be introduced to varying concentrations from sub-inhibitory levels to normally inhibitory to up to several times what would normally kill the bacteria. So the indications are, first of all, whether they grow or not in these presence of the higher levels of drug. And secondly, when we bring them back, we'll be doing genetic assays to look to see which genes might have been turned on or expressed differently in that environment.
That sounds fascinating. How did y'all come up with the idea to look into this?
Well, again, this is built on literature studies back to the studies in the literature that date back to the 1980s. It seems to be, a lot of hit and miss, one-off earlier experiments that have been done, some really interesting findings, and then for different reasons not followed up on. So we've been conducting research with bacteria for roughly 20 years now, and under various space missions and different applications. And this is just the next extension. We're really excited to see this particular one fly. I am particularly excited to see this one coming to fruition. I'm really anxious to see what the results show.
How long before you would have results? Is there a lag time to study what you get down, the data, before you are able to say anything conclusive?
Yeah, in our case, we're going up on Orbital 1 with this, and we're coming back on a couple of different SpaceX flights. So part of the payload is coming back on the, I believe it's SpaceX 3, and then the next one, SpaceX 4, if I recall correctly. So once we get the samples back, they'll be preserved in flight. Basically, the crew will go in and activate the experiments and then terminate them per a timeline. And then they're sitting there and just in stasis for the rest of the period waiting for the return flight. Once we get them back, we'll be able to begin doing the data analysis.
Do you have any previous conclusions that you've been able to to draw on why the space atmosphere affects vaccines like it does?
Well, the interesting thing here is whether or not it's unique to that environment, like a localized effect. And what happens in microgravity, the bacteria normally are in a suspension in a fluid, and they're slowly falling due to gravity on Earth. When you take gravity away, they tend to stay in the same place in the microgravity environment, and that changes the chemical makeup of what's in their surrounding environment. The technical term is reduced mass transport. Essentially, it's often referred to as the cells end up living in their dirty bathwater because molecules aren't moving away as quickly, the cell's not falling away from the excreted products, and stuff is not getting into the cell as quickly from the outside.
Wow, that's really interesting. So it must be nice to have the space station around to perform this sort of experiment on.
Oh, absolutely. I wish we could be up there doing this ourselves. It'd be even better. But it's going to be great to have the data come back, and we're really anxious to see, first of all, if the cells are able to grow as we expect they will in these levels of the drug, and then secondly, when we start looking at the genes that are responsible for how they're able to do that. Those are the two primary results that we're looking for this first round of experiments.
Well, that's great. We really look forward to hearing what you find out, and thanks again so much for talking with us. We appreciate it.
Well, thank you for having me.